So today we are going to take another step down into understanding this abstraction mechanism of processes. And I love this lecture because there's some really cool material in it. And this is one of those things, if you happen to like multi-threading, if you like concurrency, which I love. Unfortunately, probably not many of you remember Manny Chandy because I think he retired before most of you, except maybe the seniors, would have had an opportunity to have him. But he had a course on distributed systems, which I got to take the first year it was offered, and Manny was my advisor. And I've always loved concurrency, parallelism, network programming, all of that stuff. I just love it. And so this stuff really scratches one of those itches for me. So I think you'll love it too. It's just an amazing thing, especially when you start to see the nuances, the richness of the whole topic. And it's increasingly relevant now that virtually every device you might have, like I've got my stupid Raspberry Pi right here, and it's got like 2 or 4 cores in it. My phone's got multiple cores. My laptop's got 8 cores. I mean, it's just being able to do multi-threaded or actual parallel programming is so easy nowadays. So let's dive into this. Last time we talked about processes, and remember that they were called sequential processes because it was a single sequential flow of execution through the program. I just remembered I wanted to double check my audio settings. Good, everything is set. So nowadays, operating systems offer this abstraction called multi-threading. And the idea is that we can actually start multiple concurrent threads of execution in a single process. So now instead of just being a single sequential flow through the program, the process may now have many threads of execution all running concurrently, and sometimes in parallel. So this requires changing the process model. There was certain information that I talked about last time in the process context, like the register state, the program counter. And if you think about register state and program counter, you would say, oh yeah, every thread is going to be at a different point in the program potentially. So now I need multiple program counters. Every thread is going to be doing calculations, so they'll want to use the CPU. So that means each thread needs its own register state. And so you start to realize that some things get managed at the per thread level, and other things get managed at the per process level. So I have this chart here. These are in a single threaded process, the items that might be managed in the process, and it's all the kinds of things that you might think of normally. Okay. Now, when you switch to multi-threaded processes, you'll notice that some of these resources stay associated with the process and others start to be managed on a per thread basis. So the per process items are still the address space, the program text, global variables, the memory heap, because the threads are all sharing that stuff. Who the children are of the process remains on a per process basis because you don't have one child or one thread starting some children and another thread starting other children, and those things are associated with the thread in some way. But the per thread items are going to be the execution state of the program. So CPU registers, program counter, stack, and stack pointer. Okay. Hopefully that really clearly illustrates what's actually going on here. Now, one of the things that I want to mention is, because it becomes very important later on in this discussion, and it becomes extremely important next time, is that this is all the user space, user mode abstraction. So this is what the application sees. This is what the OS is exposing. How is it implemented? That's a big topic we're going to be discussing today. And so you can be sure that as we get further on into the discussion, I'm going to distinguish what the OS is exposing as an abstraction versus how it's actually implemented in the kernel. That's actually very relevant to the second project and the first Pintos assignment as well, because you need to understand what it is that you're building. Okay, why do we want multi-threaded processes? Why do we want to introduce the overhead of having multiple threads per process? Well, there's a couple of reasons why we want to. The first one is one that you'd probably think of right off the bat. Well, performance. More threads is faster, somehow. More threads is better, somehow. This is mostly true. There are certainly circumstances where it's not true. But the other reason that you may not be so aware of is that threading allows you to construct programs more easily in certain contexts. And I'll show you an example of that. You may not have ever thought, like, why are all the system calls blocking? When I read the disk, why does it block until the data is ready? When I call the network asking for data and it blocks, why does it block? Because we could create something asynchronously. I think that this may be much more in line with the way that JavaScript works, but I'd have to ask somebody because I actually know very little about JavaScript programming. It's something I've never had to learn, so I haven't learned it. But so you have the synchronous versus asynchronous type of mechanism, and most of the system calls are synchronous unless you switch them into an asynchronous mode. So we'll talk about that today. As far as performance is concerned, there's a lot of different ways that you can sort of explain performance or measure performance. Like, is it the responsiveness of an application? Is it the throughput of data or the speed with which you're able to perform calculations? So multi-threading can have a beneficial impact in multiple ways of defining performance. And responsiveness is a great example because you can always go and shove long-running slow tasks onto a thread and then do other stuff that's user-facing in another thread in the same process. And that means that the user will get responses from their interactions quickly, and that means they'll be happy. Okay, so that's a simple way that multi-threading improves the quality of life for users. And web browsers are a great example of this. I will have to say that this may not be the case any longer, but in general, most applications that do slow, long-running things like download files from the internet or do anything that might, like I have an application I've been working on that does long, large calculations, and I want to do them on a separate thread so that the app can remain responsive to the user. So you just stick that stuff on a separate thread of execution, and then you have a thread that responds to the user interactions, and the app remains interactive, user-friendly, responsive, all of those things. So here's the common web browser pattern. You have the UI thread, which takes care of updating the display version of the page as more data may become available, as files get downloaded. Probably all of you have had the experience of seeing a web page rendered without its styles until the styles are downloaded, and then it switches, or maybe in a different font until the fonts are downloaded, blah, 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 blah. This is very, very common. Okay, and so you'll have typically a pool of background threads that's handling these kinds of interactions if you don't have a web browser that's using some very clever advanced techniques, which I will also talk about later on in this discussion. So here's the question. You have these multiple threads. Let's say you have a pool of 10 threads and you're accessing a web page like CNN.com, which if you access CNN.com or any standard web page, you're probably downloading dozens, if not hundreds of files, because you have all kinds of images and other scripts and things like that to download. So does this require multiple CPUs to yield a benefit? This is a question I want you to think about. The answer to the question involves answering other questions like, well, what is the computer doing most of the time? And if you're going to retrieve a file from the internet, the answer is most of the time you're going to be spending waiting because you've got to send the request, the remote server has to respond to the request, send the response. You've got network latency going both directions. Maybe if you're lucky, you've got a ping time on the order of milliseconds. And so your computer is mostly going to be spent waiting, which means the CPU is not utilized hardly at all. So when we have multiple threads doing these accesses concurrently, what we're doing is we're taking the advantage of the time we spend waiting to start up another request. And then the time we spend waiting, we use to process a request or response that came in. So you can see that what we're doing is taking advantage of the latency of the communication to do other stuff. That's what the threads buy us. And so in this case, this context, you can have one single CPU with a bunch of threads, and you'll still see a performance improvement, because what you're doing is you're doing something useful with the time you would otherwise spend waiting if you only had a single thread, okay? So this is kind of an important result. When you have a single physical processor and you have I/O bound tasks, that's how we describe it, you will notice that multiple threads of execution give you an increased performance, because now you're able to start up multiple interactions over a network or with the user at the same time, and you can overlap the waiting periods as you do these slow operations. Here's another example. You want to do some calculation. I don't know what that might be. I love fractals. I think it's a great project because it's really fun to see the beautiful pictures that fractal generators can produce. And, as you get more deeply into fractals, the calculations can be very involved. And so you say, well, I want to improve the performance of this fractal calculation, so I'm going to split it into multiple threads of execution. So now you ask another question, or maybe the same question from the previous slide. Does this require multiple CPUs to yield a benefit? Again, you think about, well, what's the context? I have something that is CPU bound. It will use as much compute time as I have available for it. If I split that into two threads and I still only have one CPU, well, now the OS has to somehow switch, or somebody has to switch which thread is running on that one CPU. And you remember what I talked about last time, context switches are slow and they're not useful work. I mean, hopefully you all understand what I mean when I say that. Useful work is what the user wants wants the system to be doing. And so if we're not doing calculations, then the context switches slow us down. So trying to spin up multiple CPU-bound threads on a single processor is going to be slower than just running one CPU-bound thread on that single processor. And so in this case, we do need multiple CPUs to yield a benefit, okay? So I don't really develop this notion of CPU-bound versus I/O-bound very deeply, network-bound. There's different, obviously different peripherals that you could become bound on. So if you want to ask me about that later, I'd be happy to answer any questions about it. But yeah, so this is the important result. If you have a CPU-bound task and you try to run more threads than you have CPUs, you're gonna slow down your program. Now, I would mention that hyperthreading, some of you may be saying, well, what about hyperthreading? And hyperthreading is an interesting beast because it's kind of a way of taking advantage of the superscalar processor architecture, which will have multiple ALUs, it'll have multiple memory addressing units, it'll have multiple different things, so that as instructions come into the processor will schedule which components are necessary to execute that instruction, and you can have two logical threads of execution running on the same processor because most of the time they won't have two deeply conflicting requirements of processor resources. And so the rule of thumb is that a logical thread or a hyperthreading processor gets about 1.5x threads running at the same time, because there are sometimes conflicts in the way the threads execute. So you will still see benefits there, not as much as if you have two separate cores. And there's a bajillion other things that affect it as well, including hardware caching, because a lot of times these multi-core systems have multiple processors sharing a cache, and that also has an effect. Okay, but anyway, rule of thumb, if you have multiple CPUs in the system, a single threaded process will not be able to take advantage of multiple CPUs. That should just be obvious. you have to somehow construct your program to know how to use multiple processors. And in general, you would want to run as many threads of execution as you have processors. You don't want to go above it if they're all CPU bound, because then you won't get any benefit of it, and you'll probably see a deficit. Okay, a little bit more about this. Yeah, so I've mentioned these terms a little bit already, concurrency and parallelism. Concurrency means that you have multiple tasks that are overlapping in some way. We have this phrase that we use, logical control flows. You can think of a logical control flow as a path of execution through your program as it does things. So obviously that depends on the data it's processing. It depends on the number of things, but it has a logical control flow through the program, and having multiple of those things overlap is concurrency. It does not require multiple processors. And it happens all the time in I/O tasks. Okay, so as I say here, a one CPU system can achieve this by switching back and forth between concurrent tasks, understanding that they may be interleaved in unusual ways that can lead to bugs. And that's the challenge of writing multi-threaded programs. Okay, so concurrency doesn't necessarily imply that multiple task instructions are being executed at the same time. Concurrency does not necessarily mean that two things are happening at once. At a high level they are, but at a low level they may still be executing in sequence. We just have this illusion of things happening at the same time. Now, parallelism means that multiple tasks are actually occurring at the same time. It requires multiple processors, or hyperthreading certainly would produce this as well, but we have to have the ability to resolve multiple instructions at the same time. Okay, if you have multiple cores, you can have parallelism. If you only have a single processor, you can only have concurrency. And it's interesting because it means the kinds of bugs that you can manifest in a parallel or concurrent program are different. So that's one of the interesting issues, is that if you're actually writing a program that should be able to operate in parallel, then you kind of need to test it on a parallel computing platform to make sure that it behaves correctly. So there's, even better is to prove that it doesn't have bugs, but if you can't, then executing it on a parallel system will expose more bugs than just on a single core system. Okay, so we had this large scientific mathematical computation, and so we're going to split it into multiple threads. If we have multiple CPUs, we can put one thread on each CPU so that they actually run in parallel. And so this is where we run into an interesting result, which is that let's assume that the program takes 1 unit of time to run on a single CPU. And so you say, well, if it takes 1 unit of time to run on one CPU and I put it on n CPUs, ideally it takes 1 over n the time to complete. That would be nice. That would make sense. That would be a wonderful world to live in. I want it to be 10 times faster, I run it on 10 CPUs. I want it to be 100 times faster, I run it on 100 CPUs. So the problem is that the structure of the program affects whether or not this speed up actually occurs. Because almost always you have a portion of your program that has to execute sequentially, and then you have another part of the program that can be parallelized. And the part that has to execute sequentially comes to dominate the performance of the program as you add processors. I mean, that's kind of an obvious statement if you think about it. Sequential part can't be split up. The parallel part can be. So the ratio of those two things is going to affect how much performance improvement you get from adding processors. So there's this law called Dahls Law, which is it actually can be applied in many different contexts. I have a great program that shows where Dahls Law applies even in a single core program, where you have I/O concurrency. So, it's quite a useful law to know when you're trying to work on performance improvement. But you have S as the percentage of the tasks that must be executed serially. On a single processor machine, that'll take 1 unit at a time. On an n processor machine, notice S is the sequential part. This is not complicated. If only all math was this simple. And 1 minus s is the parallel part that can actually be divided over the n processors. And so this is going to be the speed up due to parallelism. It's just 1 over the amount of time it takes to run. And so if you have a task with 10% that has to be run serially, it's kind of shocking. The best performance improvement you can get as you throw CPUs at this is 10x. And so when you're trying to improve the performance of a multi-threaded program, you want to try to shrink that sequential part as much as you can, because that will maximize the payoff from running on multiple cores. I had an experience like this when I was a much younger software engineer, and I had a friend who was doing simulations, and his program had a large sequential component. And his professor bought him this big, powerful computer with like 8 cores in it. And I thought, well, this is going to be great. And he threw all this compute power at it, and it only sped up by like 2 to 3 times. It was like, oh man, we have a big sequential component that we need to work on to get it to run more efficiently on the parallel computer. Okay, now the caveat about Dahls Law is that it's for fixed size tasks. And so there's an interesting aspect of this, that as you give people more compute power, they don't keep the tasks fixed size, because they say, I've got more compute power, I'm going to increase the resolution of my simulation, I'm going to decrease the time step so that I have a more accurate simulation. But basically, people will scale up the problem they want to solve when the compute hardware becomes more powerful and more sophisticated. So most of the time, you aren't actually governed strictly by the narrow definition or the constraints that Dahls Law seems to require. And so the interesting thing is, as you take the task and you scale it up, well, the sequential part will be growing at a certain pace, and the parallel part will be growing at a certain pace. And almost invariably, with these kinds of tasks that we parallelize, the parallel part grows much faster than the sequential part. So this is why we still have large compute clusters for doing large-scale computational problems, because as we grow the scope of the problem, most problems have this nice benefit that the parallel part grows faster than the sequential part. So we keep getting a benefit by throwing more processors at it. And so this is called Gustafson-Barsis law, and it's just another aspect of Dahls Law. It's not really like a refutation or anything like that. It's just understanding the benefits you get, the performance benefits you get from parallelism, from different approaches or different aspects of the same kind of constraint. It looks like there's a question.
Yeah. So with like the parallel and sequential components of a program, so I know that like GPUs have like a ton of cores, and like they're really suited to like parallel programming. But I guess if you're playing like a video game or something, like obviously there's gonna be like sequential components. So I was wondering, do those sequential components like run on the CPU and then it sends like the parallel tasks, the parallel components to be like run on the GPU, or is it like
Yeah,
a different way?
that would be about right. But it's not just that. Like if you're talking about games specifically, because games have certain things that are well suited to GPUs. I mean, 3D graphics or 2D graphics are an obvious part of that. But audio processing, if they're doing anything sophisticated with audio, would be moved onto the GPU. Anything with like particle system simulation would be moved onto the GPU. If you have any fluid flow, it would be moved onto the GPU. So that's one aspect of the picture. Now, one thing where I'm not very familiar with is how easy or hard it is to set up multiple independent tasks on a GPU and run them concurrently, so that you're taking advantage of GPU parallelism separately. But the other thing is that besides the sequential tasks that would run on the CPU, you also have a lot of I/O tasks. If you have user interactions, mouse, keyboard, those kinds of things, they kind of have to be on the CPU. And then you also have any kind of networking operations. So even on the CPU, you'll see a breakdown of tasks into multiple threads, if it makes sense to isolate them from each other and then have specific well-defined integration points. But The overall sense that you have is correct, that you're going to see the bulk of the sequential stuff happening on the CPU. And a well-written game is going to try to parallelize as much as possible. But the specifics of how easily that is to be achieved, I have to confess ignorance on that one, because I'm only learning GPU programming right now. I have a long way to go on that one. So I hope that answered your question.
Yeah, thank you.
Cool. All right, let's see. Oh yeah, so another couple of benefits that you get from multi-threading is these things called resource sharing and economy. Now you might say, well, what in the world does resource sharing and economy have to do with multi-threading? That seems to make no sense. But if you understand what's meant by these terms, it starts to make a lot of sense. Threads are a lot cheaper to create and destroy than processes are. Processes require more resources to be managed. And so threads, like starting up yet another thread in a program, tends to be a lot cheaper than spinning up a whole new process. And so that's a nice benefit of using threads instead of using processes. Also, it tends to be that context switching between threads in a process is cheaper than context switching between processes. And the reason why is because of the address space isolation. That's sort of one of the number one places where you see a big benefit of cheaper context switches, is because you don't have to change address space configuration. Also, the second thread is probably going to be able to leverage cache data that the first thread had already brought into the cache, the hardware caches. So you get some benefits, and some OS schedulers will actually prefer scheduling another thread in the same process over a separate process because of some of the performance benefits that are achieved from doing so. Okay, let's see. Sharing resources. Well, when you're in the same address space and you're in the same process, it's very easy to share OS allocated resources. That should be pretty obvious. It's not too difficult to do resource sharing across processes. You all saw that with the command shell, because when the parent sets up resources and then forks, the child has access to all the same resources. If you're talking file descriptors and so forth. Shared memory is the same way, but it's just a lot easier with threads. You have a lot fewer steps to go through. Okay, cleaner abstractions, and this is one of the big comments that I want to make today, because you'll see a lot of important reasons why we like to construct system software the way that we do. So why do we have long-running system calls that block? The first thing is that they're just easier to think about. I'm going to ask for data, presuming that I need that data to continue. If I just wait until the data shows up and then I can proceed, it's easier to reason about that kind of system. There's the alternative, which I have on the slide, is non-blocking operations, where I say I want this data, and the OS says, okay, and then you have to figure out what to do with yourself while you wait, and you have to periodically come back and say, is the data available yet? Well, that's just more complicated to construct. And like I said, I think this is much more of the JavaScript web client kind of model that's used, but I'm not super familiar with it. I'm going to have to ask an expert in this area so that I can understand that a little bit better. But you basically monitor the thing that you wanted to complete until it's done, and then you can go ahead and complete that part of your task. So it's a very different approach. And so blocking code that uses blocking operations is just easier to write. It's just simpler to think about. Okay, here are some examples of asynchronous I/O support in the OS kernel. So you have this call called select, which you can see you give it a number of file descriptors. You give it the file descriptors that you're interested in reading. You give it a collection of file descriptors you're interested in writing. You have a collection of file descriptors that you're interested in anything else happening on them, and how long to wait to find out if something interesting happens. And poll is similar, except it kind of throws all the file descriptors into a single collection. And so what these calls do is the user application is saying to the OS, I want you to tell me when anything interesting happens on any of these file descriptors. And when the OS returns, you know that there is at least one thing you can do. Maybe data showed up, maybe data got sent and the send buffer is now empty. Maybe a socket got closed, maybe a file got closed, something like that. And so applications can leverage these kinds of operations to build very high performance implementations, because the OS and even the hardware is engineered to make these kinds of things super fast so that you can monitor tens of thousands of sockets concurrently, and it will be a constant time operation. So that's how this kind of stuff is used. It does increase complexity. The simple example that I like to walk through is a web server. If you think about how a web server works, you got the client, he's connecting to the web server, he sends a request, an HTTP request for a given file. And so what the server has to do is listen for a socket connection. That gets established. We're ignoring SSL, we're ignoring all the other stuff that happens these days, but you have the connection is made, and the server receives the connection. That's going to be blocking read calls. It's going to look up the data that's necessary. That will be blocking disk operations. And then it will stream out the data as well as it can. So those are blocking write calls to a socket. And then eventually the operation completes, it'll close the socket unless there's some pipelining going on between the client and the server. Now we want to do this as fast as possible. And that means overlapping concurrent requests, because we know that most of the time in this process is spent waiting. So why not overlap them? So if you were to implement a web server, you could ask yourself, how would it look if I did this in multiple different strategies, multiple different approaches? Single-threaded process with blocking I/O calls, single-threaded process with non-blocking I/O calls, and multi-threaded process with blocking I/O calls. And you could think to yourself, how fast would it be? How easy would it be to write? How easy would it be to maintain? So single-threaded, I bet all of us could figure that out. You know, if I gave you like a month, I bet you could all come back and have that implemented, because really it's not that much more complicated than a command shell. In fact, parts of it are probably easier. So you write a loop that processes each request. So in the main loop, you would have a listen call that's waiting for socket connections to be made. And then inside that thing, do I actually have it on the slide? I can't remember. But no, it doesn't look like I do. So receive, so it reads all the data till it has a whole request. It does the thing that the request asks for, probably sending out a file as a response, closes the connection, and then goes back and listens again for the next request or next connection. While the web server is processing a given request, it can't do anything else, because you always have these blocking calls, and you're pretty much always blocked. So you can see that this is going to be slow. It's going to be hella slow, because we have a single-threaded web server that's doing things sequentially, and all the operations are blocked. It can't take advantage of the time it spends waiting. Now, if we switch to non-blocking I/O, now we can start getting some concurrency. But the problem is we'll now have these multiple connections that are all being serviced at the same time by the server, and the server needs to know what it was doing with each of those connections so it doesn't lose track of what it was doing at any given time. So we can start overlapping the networking operations, which gives us concurrency, even though we still have a single thread of execution. And so a single request and response will still take the same general amount of time, but we're going to be able to overlap that request and response with a bunch of others. So we'll start seeing a dramatically increased throughput. And we'll start to see the CPU becoming the bottleneck in all likelihood, rather than the network connections. Because the server is going to be checking all the connections and seeing what it can do. It'll be calling poll or epoll or select or something like that to deal with this. Okay, so you have all these connections, and you're listening to them all and interacting with them as you're able to. And with each of these connections, you'll have some state, probably a struct or something like that, saying, what am I doing right now on this connection? What's the incoming data? And you have to accumulate this in the buffer till all the data's shown up. And then you can do stuff with it. And then you have to say, this is the output buffer to send back. And then you've got to possibly take multiple steps to send out the output data. So you have to have the state telling you where you are in the process. What stage of the request or response cycle is each connection at? Am I receiving? If so, how much data have I gotten so that you can keep appending data as it comes in? Sending the response, how much of the file has been sent, or is the web server responding with an error? These kinds of things. And so the main loop is going to do something that monitors, like with a select call or a poll call, monitoring all these connections concurrently and waiting to see if it can read or write on one of them without blocking. That's what this does. And so for each socket, you get the, so these are sockets that you can do something on. You go look at the socket's associated state. You do as much as you can, and then you go on to the next active socket. And this is basically your entire loop. But you're still doing it all with one thread. So this is an example. I don't want to spend too much time on this because there's a lot of other important things to talk about today. But you'll notice here that we're implementing concurrency in the web server, and we're taking care of it ourselves as opposed to relying on the operating system. That's the problem with having to do something like this. Okay? Now, what if we just say, I'm going to write multiple threads of execution, and I'm going to use blocking calls, and I'm just going to do it. Okay, you'll notice here that the OS takes care of the concurrency for you now, because when one thread makes a blocking call, yes, that thread gets blocked, but the OS may know some data's shown up and it can context switch to another thread and resume execution of that thread. And your program is simple. You haven't had to do anything sophisticated to manage a bunch of sockets all at once. You just build them using the threading abstraction. And it allows you to still have a concurrent program and blocking system calls. You get to have your cake and eat it too, or at least most of it. So multi-threaded web server with the blocking network I/O would basically be identical to the single-threaded version with a little bit of coordination for any shared resources, and that would be it. So hopefully everybody can see how having multi-threading allows you to construct programs in a simple manner that allows you to take advantage of blocking system calls, because the OS is clever enough to switch to something else when a blocking system call is made. So that's the whole point. Okay, I don't know if there's any questions about this, but if you have any questions, I want you to ask them, because this is kind of an important detail. I want to mention one other thing in the context of this comparison, because it might sound like I'm really down on asynchronous I/O. It turns out that you can build some really powerful and efficient systems using the async approach. It's just complicated. That's it. So there are a lot of examples where this is pursued. One of the examples, I'm going to just throw this up here, Nginx. That's how you pronounce that weird sequence of consonants and one vowel. Nginx is a web server. I think that there's other web servers that are more popular than Nginx by now. But Nginx was kind of revolutionary when it was created, because it was designed to solve a problem that we had back in the 90s, which was that our nice, simple, understandable, multi-threaded approach with blocking system calls to writing web servers would allow you to support hundreds of users, maybe thousands if you're super lucky. So I'm talking concurrent connections. But what we'd really like to do is support tens of thousands of concurrent connections, 20,000, 30,000, 40,000. And so the asynchronous non-blocking approach allows you to get up to 30,000, 40,000 concurrent connections. But it's just, you saw the pattern that I showed you on the previous slide. You've got to have state associated with every connection, and you've got to manage a concurrency yourself. If you're fine doing that, you can create an incredibly sophisticated system. There was one project I did which was super fun, and you had a piece of software that had to talk to a bunch of different clients all at the same time. And the previous generation of that program was written to use thread per connection with blocking calls, and it could support several hundred clients, maybe up to a few thousand, but it was really, the system would start to groan. I went in and I wrote a version like what I just described on the previous slides using asynchronous IO and socket polling mechanism. And I was able to easily support 40, 50,000 concurrent connections because a lot of the time was being spent waiting, and it's a very low resource overhead. So multi-threading and OS concurrency is easy to maintain, easy to think about, but there is also a huge benefit to going the async route. And so I don't want anybody to think that I'm dismissing it out of hand. It's just horses for courses is what I always say. Okay, I don't know if there's any questions about any of that. Doesn't seem like it. All right, well, if anybody has any questions, feel free to shoot. Otherwise, I am going to go on and talk about how do we implement these little beasties. Because it turns out that we have multiple places that we can build this threading abstraction. We could build threads entirely in user mode and user space. It's not that hard. C and the standard library and OS kernels provide mechanisms for building user space threading. In fact, I don't think it is anymore in CS24, but one of the old CS24 assignments was build a user space threading library with cooperative multitasking and then later preemptive multitasking, which is pretty cool that you can even do it. It's pretty freaking amazing. But anyway, the kernel is only providing processes. Okay, notice down here on the picture, it's only providing processes with all the strengths and limitations of that. The threading library is in the process providing thread scheduling. And so this is useful when you have an OS that doesn't support kernel threading, which happens very rarely by now because it's a very common thing to provide in an OS now. These libraries tend to have to provide cooperative multi-threading because in user space, it's not really possible to build a software. I'm sorry, let me think of the correct way of expressing this. The kernel tends not to expose a very high resolution timer mechanism to user processes because of the overhead of doing that. It may have a high resolution internal timer, but it may not expose that because then you're wasting a ton of time invoking a certain user process all the time. Okay, so that tends to be cooperative. Now, this is nice because you're just switching around inside the user process. You're not trapping into the kernel. Remember, trapping into the kernel is not the fastest thing to do. You're not invoking the kernel to context switch, save machine context, restore machine context, any of that. You're doing it all in your own program, so it's very fast. The problem is you can't use user space threading to achieve parallelism on multiple cores because that tends to be something the OS has to do for you. So you tend to be relegated to a single CPU, which means that, well, okay, maybe user threading is good for long-running tasks. Well, the problem is when you do a long-running task, you trap into the kernel because the kernel takes care of it for you. And what's the kernel going to do if it notices you're about to do a long-running task? It's going to context switch to another process, which means your user space threading library just lost control. So user threading is really limited in its capacity to do things. So user threading is awfully limited. Okay. Now, another possible approach is to actually support threads of execution in the kernel, which is what most OSs do by now. And so the kernel now has multiple choices in how it supports threading on behalf of user programs. Okay. Now, I've already talked about this. If a user program does a long-running call, well, if it has multiple threads of execution in the process, then it may be that the kernel can context switch to another thread in the same process, and that will be more efficient. I mentioned this earlier on. I don't have to change the address mapping. I don't have to worry. Why? In fact, I gain a benefit of anything in the hardware caches for that process by context switching to another thread. Okay. On a multiprocessor system, kernel threading support means that a process that wants to take advantage of multiple cores can do that because the kernel can schedule multiple compute-intensive threads on different processors. So you start getting a lot of benefits. The big drawback of kernel threading is that you have to trap into the kernel when you want to do any of these threading operations because the kernel has to know about it. And so if your kernel trap mechanism is slow or any other parts of the interaction with the kernel is slow, then your thread management is also going to be slower. What can you do? It's like it's worth the cost. And so that's why virtually every operating system has kernel threading support built in. Okay. Now the OS provides this multitasking support. So this is where this is going to be very relevant to the second project. There's a thing called a schedulable kernel level task. Okay. There's a nickname for that. We call it a kernel thread. And so when the kernel works, and this is one of those little secrets of OS implementation, when you implement a multi-threaded, or let me think of the right way of a multitasking OS, we'll call it that way. That's the correct way of describing it. The way that the OS does that is by having multiple kernel threads that it can run, and the OS scheduler just switches between kernel threads. Some of those kernel threads are associated with processes, or they will be associated with user threads in processes. But the kernel thread is the thing that the OS kernel actually manages. Okay, so that's why I say here the threads context has CPU registers, program counter, blah, blah, blah. And this kernel thread is not a process. It's not necessarily a thread in a process either. So there has to be some association between processes and kernel threads or process threads and kernel threads. Okay, but the kernel thread is the thing the OS implements to provide this concurrency abstraction. You may even have kernel threads that don't correspond to a user process because they're used to do utility operations like disk flushing and things like that. Like I've got my file system cache and some pages are dirty and I have a kernel thread that goes through and writes some of those dirty pages so that if power goes out, I'm a bit more robust. You may have situations like that. The kernel threads can be used in many different ways. Okay. All right. So we're not going to be able to get very far into this, but I'm going to try to at least do a really high level discussion and you can read the rest. It's not super complicated. But one of the things the OS implementer has to decide is how to map these kernel threads, which are the actual concurrency mechanism in the kernel, to user processes and user threads. Okay. And there's three different models that you can consider. One is a many-to-one model where all the user threads are mapped to a single kernel thread. Now, the way we would say this is all the user threads in a single process are mapped to a single kernel thread. And so the kernel thread is associated with a process so that we can schedule multiple processes concurrently, but the threading has to be provided by the application itself. So this is the user mode threading implementation. Okay. And the GNU Portable Threads library is an example of a library that follows this model, many to one. So we worry about scheduling processes, and the kernel doesn't know about anything more fine-grained than that. Then we have a one-to-one threading model, which basically associates every user thread in a process with one kernel thread. And that's the standard model that we use day to day now in modern operating systems. Linux uses it, Mac OS uses it, okay? And so, yeah, as I say on the slide, this is corresponding to the kernel supported threading library. So a single user thread in a process can make a blocking call. That corresponding kernel thread becomes blocked, but other user threads are able to proceed in the same program because those the corresponding kernel threads are able to continue executing. They don't become blocked. I hope this makes sense. It's going to become more important in the third project, but in the second project, you're actually living entirely in the kernel and you're working on the kernel thread abstraction, which is a pretty cool thing to be doing, to be honest. I hope you have fun. It's going to be really cool. So yeah, this is the model that most OSs provide because it's straightforward to implement. Okay, the last one that I want to talk about, and I'll just introduce the notion and you can read about it more later on, is a many-to-many or hybrid threading model where you have some number of kernel threads and some number of user threads, and typically the number of kernel threads is less than the number of user threads, and the OS now has a complex problem to solve of how to map user threads to a smaller number of kernel threads. There are benefits of doing this. Notice that I say here in the premises, both user mode threading and kernel threading have benefits. User space threading is lightweight and inexpensive. You don't have to talk to the kernel, but it's limited. And so a hybrid threading model tries to achieve the benefits of both approaches to threading, but it's just super expensive. Okay, let me go ahead and throw this up here because I just want to show you, there's a picture right here. The challenge that you have with this hybrid model is that the user space threading library has to have a scheduler, and the kernel also has to have a scheduler. And somehow we have to pass information between the two to make sure that both schedulers are making good decisions about mapping user threads to corresponding kernel threads. Okay, as the picture indicates, you may have more user threads than you have kernel threads, and you want to make sure that you map things intelligently. Okay. The last thing that I'll mention here is that Windows, since Windows 7, has been using a hybrid threading model. Unfortunately, Windows being a commercial enterprise doesn't share a lot of information about how this has worked for them. I'm really curious whether or not it's paid off as an approach because I'm sure it's more complex and generates some challenges for them. Anyway, maybe I'll show you just this one more, which is that we have to build a special communication mechanism between these two. And you can read the rest of the slides to see how people have gone about that, but it's beyond the scope of what you need for the assignment. So I think I should probably wrap. Okay, if anybody has any questions, I'll hang out. Otherwise, I will see you on Wednesday and we'll get more into this kernel threading implementation thing. See ya.